Dark matter makes up 85% of all matter in the universe. It does not emit light, it does not reflect light, it does not absorb light, it does not block light. And yet scientists using the James Webb Space Telescope just mapped it with unprecedented precision. Right now, 255 hours of JWST observations have produced the highest resolution dark matter map ever created, published January 26, 2026 in Nature Astronomy. And the data confirms something cosmologists have suspected but never proven at this scale. Dark matter and ordinary matter coexist in perfect alignment across cosmic history. The map contains nearly 800,000 galaxies. That is twice as many as Hubble detected in the same region, and 10 times more than any ground-based observatory. The spatial resolution is at least 1 arc-minute, sharp enough to reveal structures that were completely invisible in previous surveys. Wherever a massive galaxy cluster exists, an equally massive concentration of dark matter is present. The correlation is 1-to-1, not approximately, not mostly, exactly. Dense regions of dark matter are connected by lower density filaments, forming a web-like structure spanning millions of light years. And ordinary matter, gas, dust, stars, planets, traces that same structure. Dr. Diana Scognamiglio from NASA's Jet Propulsion Laboratory, lead author of the study, stated, "Previously, we were looking at a blurry picture of dark matter. Now we're seeing the invisible scaffolding of the universe in stunning detail. Still more striking. The map extends back to redshift 2, approximately 10 to 11 billion years ago, during the epoch known as cosmic noon, when the universe was forming stars and galaxies at its highest rate. Dark matter structures at cosmic noon look fundamentally similar to dark matter structures today. The cosmic web was already in place. JWST revealed what simulations predicted, but observations could not confirm. Dark matter shaped the universe first, and ordinary matter followed. Here is what should concern you most. If dark matter concentrations determine where galaxies form, and we now have a map showing exactly where those concentrations exist across 11 billion years of cosmic history, we can finally test whether our models of structure formation are correct, or if something fundamental about how the universe assembled itself has been wrong this entire time. Think about that. Before we break down how scientists mapped the invisible, if you want to stay updated on discoveries that rewrite our understanding of how the universe is structured, hit subscribe and turn on notifications. Because what we are about to explain will change how you think about the space between galaxies and the forces that built everything we see. Leave a comment telling us, did you know that billions of dark matter particles pass through your body every second? Let's start with what dark matter actually is, or more accurately, what we know it is not. It is not stars, it is not gas, it is not dust, it is not black holes, at least not in sufficient quantities to account for the observed gravitational effects. It is not any form of ordinary matter made of protons, neutrons, and electrons. Dark matter is something else, a particle or field that interacts with the universe almost exclusively through gravity. It does not interact electromagnetically, which is why it does not emit, absorb, or reflect photons. It passes through ordinary matter like a ghost. Right now, billions of dark matter particles are streaming through your body, through the Earth, through the Sun, and continuing outward into space without interacting with a single atom. Dr. Richard Massey emphasized this point. Billions of dark matter particles pass through your body every second. There's no harm, they don't notice us and just keep going. But the whole swirling cloud of dark matter around the Milky Way has enough gravity to hold our entire galaxy together. That statement is not hyperbole. If you could somehow remove all the dark matter from the Milky Way instantaneously, the galaxy would fly apart. The Sun orbits the galactic center at approximately 220 kilometers per second. At that speed, without the gravitational binding provided by dark matter, the Sun and every other star in the outer regions of the galaxy would escape into intergalactic space within a few hundred million years. The Milky Way's disk would unravel. Spiral arms would disperse. The galaxy as we know it would cease to exist. And yet, individual dark matter particles pass through us undetected. The reason is simple. Gravity is extraordinarily weak on the scale of individual particles. A single dark matter particle has negligible gravitational influence. But when trillions upon trillions of dark matter particles are distributed in a halo around a galaxy, their combined gravity is immense. That is how dark matter works. Weak on small scales, dominant on large scales. We know dark matter exists because we can see its gravitational effects. Galaxies rotate faster than the visible mass alone would allow. galaxy clusters hold together with far more gravitational binding energy than their stars and gas can provide. The cosmic microwave background shows temperature fluctuations that require more mass than we can see to seed the formation of large-scale structure. The evidence is overwhelming. Dark matter is real. It makes up approximately 27% of the universe's total energy mass content. Ordinary matter, everything we have ever seen, touched, or measured directly, makes up only about 4%. The remaining 69% is dark energy, an even stranger phenomenon responsible for the accelerating expansion of the universe. But knowing dark matter exists and knowing where it is located are two different problems. Until now, maps of dark matter have been limited by resolution, sensitivity, or sky coverage. Ground-based telescopes lack the angular resolution to detect the subtle distortions dark matter creates in galaxy shapes. Hubble had the resolution, but could not observe faint, distant galaxies efficiently. JWST changes that. But the mysteries don't stop there. The technique used to map dark matter is called gravitational lensing. Einstein's general relativity predicts that mass curves space-time. Light traveling through curved space-time follows the curvature. When light from a distant galaxy passes near a massive object, like a galaxy cluster or a concentration of dark matter, the light's path bends. This bending has two observable effects. The first is strong lensing, where the distortion is so extreme that the background galaxy appears magnified, stretched into arcs, or even duplicated into multiple images around the massive object. Strong lensing is dramatic and easy to identify. Astronomers use it routinely to study extremely distant galaxies that would otherwise be too faint to detect. The second effect is weak lensing. Here, the distortion is subtle. A galaxy that should appear circular looks slightly elliptical. A galaxy that should appear in one location is displaced by a fraction of an arcsecond. The effect is so small that no single galaxy can reveal it. You need to measure the shapes and positions of hundreds of thousands of galaxies to detect the statistical signal. That is what Dr. Scognamiglio and her team did. They analyzed approximately 250,000 galaxies in the JWST images, measuring how their shapes were distorted by the intervening dark matter between them and Earth. By correlating those distortions across the entire field, they reconstructed a map showing where dark matter is concentrated. The JWST data also revealed strong lensing systems. A separate team analyzing the same Cosmos Web images identified over 100 strong gravitational lenses in the field, more than doubling the number previously known. Those lenses provide independent confirmation of dark matter concentrations. Wherever strong lenses appear, massive dark matter halos must be present. The Cosmos Web Lens Survey, known as COWLS, cataloged those lenses and is using them to study both the lensing dark matter halos and the highly magnified background galaxies they reveal. Strong lensing and weak lensing are complementary techniques. Strong lensing provides precise measurements of dark matter mass in individual halos. Weak lensing provides statistical measurements of dark matter distribution across large areas. Together, they give a complete picture of how dark matter is structured from the smallest galaxy-scale halos to the largest supercluster-scale filaments. The math is complex, but the principle is straightforward. If you know the intrinsic shape of a galaxy, and you measure how that shape appears distorted, you can calculate how much mass lies between you and that galaxy, and where that mass is located. Do this for hundreds of thousands of galaxies at different distances, and you can build a three-dimensional map of dark matter distribution across billions of light years. Here's where it gets really strange. The region of sky mapped by JWST is called the Cosmos field. Cosmos stands for Cosmic Evolution Survey. It covers approximately 2 square degrees of sky in the constellation Sextans, about 2.5 times the area of the full moon. That might sound small, but in astronomical terms, it is enormous. Mapping 2 square degrees at the depth and resolution JWST achieved requires extraordinary observing time and computational resources. The Cosmos field has been studied by at least 15 different ground and space-based telescopes. Observations span wavelengths from X-rays to radio. The goal is to create the most comprehensive multi-wavelength survey of a contiguous patch of sky ever assembled. Astronomers use Cosmos to study galaxy evolution, star formation, black hole activity, and large-scale structure across cosmic time. The first dark matter map of the Cosmos field was published in 2007 using data from the Hubble Space Telescope. That map was revolutionary. It was one of the first large-scale demonstrations that weak lensing could trace dark matter distribution with enough precision to test cosmological models. Dr. Richard Massey from Durham University led that effort, along with Dr. Jason Rhodes from NASA's Jet Propulsion Laboratory. Dr. Catherine Haymans, now Astronomer Royal for Scotland at the University of Edinburgh, was part of the team that developed the techniques used to create the 2007 Hubble map. She stated, "It was really pioneering work. People were saying that there's absolutely no way you can measure a 1% distortion with everything else going on. The 2007 map proved them wrong, but it had limitations. Hubble detected approximately 400,000 galaxies in the cosmos field. Ground-based surveys detected about 80,000. The angular resolution was limited by Hubble's mirror size and the wavelengths it observed. The depth was limited by exposure time. JWST changes all of those constraints. And then something that no previous telescope could achieve happened. JWST observed the cosmos field for a total of 255 hours using its near-infrared camera, known as NIRCam. That is over 10 days of continuous observation time spread across multiple observing windows. NIRCam is optimized for infrared wavelengths, which allows it to detect galaxies that are too faint, too distant, or too obscured by dust for Hubble to see. The observations were part of a larger program called Cosmos Web, one of JWST's Cycle 1 Treasury programs. Treasury programs are large-scale surveys designed to produce datasets valuable to the entire astronomical community, not just the original proposers. Cosmos Web was led by an international team of astronomers and aimed to survey the cosmos field across multiple infrared wavelengths, building on decades of previous observations. JWST's mid-infrared instrument, known as MIRI, also contributed data to Cosmos Web. MIRI observes longer wavelengths than NIRCam, from 5 to 28 microns. Those wavelengths are particularly sensitive to dust-obscured star formation and active galactic nuclei. While MIRI data was not directly used for the weak lensing analysis described in the Nature Astronomy paper, it provides critical context for understanding the physical properties of galaxies in the cosmos field. The result? Nearly 800,000 galaxies identified in the JWST images. That is twice as many as Hubble and 10 times more than ground-based observatories. The increase in galaxy count directly translates to higher statistical power for weak lensing measurements. More galaxies mean better constraints on dark matter distribution. But it is not just the number of galaxies, it is also their distances. JWST's infrared sensitivity allows it to detect galaxies at redshifts beyond 2, corresponding to look-back times of 10 to 11 billion years. That epoch, called cosmic noon, is when the universe was forming stars at its peak rate. Understanding how dark matter was distributed during cosmic noon is critical for understanding how galaxies grew and evolved into the structures we see today. Dr. Bahram Mobasher, a distinguished professor of physics and astronomy at UC Riverside and a founding member of the Cosmos Project, explained, "The JWST dark matter map is deeper and has higher spatial resolution compared to the initial map we made using Hubble Space Telescope data. The spatial resolution of the new map is at least 1 arc-minute. For comparison, the full moon spans about 30 arc-minutes. 1 arc-minute is 1/60th of a degree. At the distances relevant to the cosmos field, 1 arc-minute corresponds to physical scales of a few 100,000 to a few million light-years, depending on redshift. That resolution is sufficient to resolve individual galaxy clusters and the filaments connecting them. But there's another problem that nobody expected. The alignment is perfect. Wherever massive galaxy clusters exist, massive concentrations of dark matter are present. Not nearby, not in the same general region, in exactly the same location. The correlation is 1-to-1 with no measurable offset. Dr. Richard Massey stated, "Wherever we see a big cluster of thousands of galaxies, we also see an equally massive amount of dark matter in the same place. And when we see a thin string of regular matter connecting 2 of those clusters, we see a string of dark matter as well. This is not a coincidence. The alignment confirms that dark matter's gravity has been pulling ordinary matter toward it throughout cosmic history. The process began shortly after the Big Bang, when tiny fluctuations in the density of dark matter began to grow through gravitational collapse. Those density fluctuations became gravitational wells. Ordinary matter, initially in the form of hydrogen and helium gas, fell into those wells. As the gas accumulated, it cooled, fragmented, and eventually formed the first stars and galaxies. The cosmic web structure visible in the JWST map is the direct result of this process. Dense regions of dark matter, called nodes, correspond to galaxy clusters. Lower density filaments of dark matter connect the nodes, and galaxies string along those filaments like beads on a thread. The voids between filaments are regions where dark matter is sparse, and correspondingly, galaxies are rare. The map shows this structure extending back to redshift 2. That means the cosmic web was already largely in place 10 to 11 billion years ago, during cosmic noon. The universe did not transition from a smooth, homogeneous state to a web-like structure gradually over time. The web formed early, and galaxies have been following the dark matter scaffolding ever since. Here's where the comparison becomes critical. The 2007 Hubble map showed hints of the cosmic web, but lacked the resolution to reveal fine structure. Features appeared blurred. Filaments were thick and indistinct. Some dark matter concentrations could not be separated from their neighbors because the angular resolution was insufficient. The 2026 JWST map resolves those features. Filaments are sharp. Galaxy clusters appear as distinct, tightly bound concentrations of dark matter. Lower mass structures that were completely invisible in the Hubble data are now clearly detected. The increase in resolution is not incremental. It is transformative. Dr. Scognamiglio described the difference. This is the largest dark matter map we've made with Webb, and it's twice as sharp as any dark matter map made by other observatories. The sharpness allows astronomers to test theoretical predictions with far greater precision. Cosmological simulations based on the lambda cold dark matter model predict specific patterns in how dark matter should be distributed. They predict the sizes, shapes, and separations of dark matter halos. They predict the density profiles of filaments. They predict how quickly structure grows over time. The JWST map allows direct comparison between those predictions and observations. So far, the agreement is excellent. The observed cosmic web matches the simulated cosmic web in remarkable detail. That agreement is strong evidence that the lambda cold dark matter model is correct, at least on the scales probed by this map. And the data showed something that simulations hinted at, but observations had not confirmed. The density contrast between nodes and filaments is higher than expected. Nodes, the densest concentrations of dark matter, contain more mass relative to the filaments than some models predicted. That has implications for galaxy formation. Galaxies in dense environments experience different evolutionary pressures than galaxies in low-density environments. They merge more frequently. They accrete gas more efficiently. Their star formation histories differ. Understanding those differences is one of the primary goals of Cosmos. By correlating the dark matter map with observations of galaxy properties, stellar masses, star formation rates, morphologies, chemical compositions, astronomers can determine how environment shapes galaxy evolution. The JWST map provides the most accurate environmental context ever achieved. Dr. Gavin Leroy from Durham University stated, "By revealing dark matter with unprecedented precision, our map shows how an invisible component of the universe has structured visible matter to the point of enabling the emergence of galaxies, stars, and ultimately life itself." Now let's put everything together. JWST observed the cosmos field for 255 hours. The near-infrared camera detected nearly 800,000 galaxies, twice as many as Hubble, and 10 times more than ground-based observatories. Approximately 250,000 of those galaxies were used for weak lensing analysis to reconstruct the dark matter distribution. The resulting map has twice the angular resolution of any previous dark matter map. It extends to redshift 2, probing dark matter structures during cosmic noon 10 to 11 billion years ago. The map reveals a 1-to-1 correlation between dark matter concentrations and galaxy clusters, confirming that dark matter's gravity has shaped the distribution of ordinary matter throughout cosmic history. The cosmic web structure, dense nodes connected by filaments with voids in between, was already in place during cosmic noon. The combined dataset confirms that lambda cold dark matter accurately predicts the large-scale structure of the universe. No anomalies, no unexplained deviations. The model works. We are not saying that dark matter is fully understood. We still do not know what particle or field constitutes dark matter. We do not know its detailed interactions beyond gravity. We do not know whether it decays, whether it has substructure, or whether there are multiple types of dark matter particles. But we do know, with far greater confidence than before, that dark matter exists, that it is distributed in a cosmic web, and that ordinary matter has been following that web for at least 11 billion years. Dr. Heyman stated, "Before we only had dark matter simulations and I always wanted to be able to see it. Now we can. And here is what this really means. The invisible scaffolding of the universe is no longer entirely invisible. We cannot see dark matter particles directly. We cannot photograph them, but we can map where they are, how much mass they contain, and how they have shaped the cosmos. That map is now the most detailed ever created. So what do we know for certain? Dark matter makes up 85% of all matter in the universe. It interacts with ordinary matter primarily through gravity. JWST has mapped its distribution across the cosmos field with unprecedented resolution using weak gravitational lensing. The map contains data from nearly 800,000 galaxies. It extends back to redshift 2, covering 10 to 11 billion years of cosmic history. Dark matter and ordinary matter are perfectly aligned, with a 1-to-1 correlation between galaxy clusters and dark matter concentrations. The cosmic web structure was in place during cosmic noon and has persisted to the present day. What don't we know? What particle or field constitutes dark matter? Whether dark matter has interactions beyond gravity? Whether the cosmic web structure extends to even earlier epochs, before cosmic noon? How the first dark matter halos formed immediately after the Big Bang? And whether small-scale deviations from lambda-cold dark matter predictions exist that could point to new physics. There is also the question of whether dark matter is truly uniform across the universe. The cosmos field covers only 2 square degrees. The entire sky contains approximately 41,000 square degrees. Cosmos represents less than 0.005% of the sky. If large-scale anomalies exist, regions where dark matter is distributed differently than lambda-cold dark matter predicts, they could be outside the cosmos field entirely. That is why wide-area surveys are critical. The European Space Agency's Euclid Space Telescope, launched in July 2023, is currently conducting its own dark matter survey. Euclid will map dark matter across approximately 1/3 of the sky, covering 15,000 square degrees. Its angular resolution is lower than JWST's, but its sky coverage is vastly larger. Euclid's data, combined with JWST's deep field observations, will provide a comprehensive view of dark matter distribution from the smallest to the largest scales. And here's the urgency. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will map dark matter over an area 4,400 times larger than the cosmos field. Roman's survey will cover a significant fraction of the sky, allowing astronomers to test whether the structures seen in cosmos are representative of the universe as a whole, or whether rare, large-scale anomalies exist that cosmos missed. Roman will not match JWST's angular resolution. JWST's primary mirror is 6.5 meters in diameter. Roman's is 2.4 meters, identical to Hubble's, but Roman has a critical advantage: field of view. JWST's NIRCam covers approximately 10 square arc minutes per exposure. Roman's wide-field instrument covers 0.28 square degrees, roughly 100 times larger. That means Roman can survey enormous areas of sky in the same time JWST takes to map a small patch. The trade-off is deliberate. JWST is designed for depth and resolution. Roman is designed for breadth and statistical power. Together, they provide complementary views of the universe. JWST maps small regions with extreme detail. Roman maps the entire sky with sufficient detail to trace large-scale structure. Dr. Jason Rhodes from NASA's Jet Propulsion Laboratory, who co-authored both the 2007 Hubble Dark Matter Map and the 2026 JWST map, is also involved in planning Roman's dark matter surveys. The goal is to map dark matter across billions of galaxies, not hundreds of thousands. That statistical power will allow cosmologists to detect subtle deviations from lambda-cold dark matter that are invisible in smaller samples. For example, if dark matter particles have very weak interactions beyond gravity, interactions too subtle to detect in laboratory experiments, those interactions might leave imprints on the cosmic web at the largest scales. Roman's wide-area survey could reveal those imprints. Similarly, if modifications to general relativity are needed on cosmological scales, Roman's data would provide the precision necessary to detect them. Because if Roman finds regions where dark matter distribution deviates from lambda-cold dark matter predictions, or if the cosmic web shows unexpected asymmetries on the largest scales, cosmologists will need to revise the model that has successfully explained structure formation for decades. JWST has confirmed the model on small and intermediate scales. Roman will test it on the largest scales accessible from Earth orbit. The truth is this: dark matter is no longer purely theoretical. It is mapped. It is measured. Its influence on galaxy formation is quantified. And the scaffolding it provides, The cosmic web that connects every galaxy, every cluster, every filament across billions of light years is now visible in data, not just simulations. And the only way to push that understanding further is to map more of the sky, probe earlier cosmic epochs, and wait for the next generation of telescopes to reveal whether the web we see is universal or whether surprises still await in the vast, dark structure holding the universe together. If this video changed how you think about the space between galaxies, hit like and subscribe to this channel. We are tracking the latest discoveries in cosmology as they emerge, and you will not want to miss what the Nancy Grace Roman Space Telescope reveals when it maps 4,400 times more sky. Leave a comment with your take. Did you know that dark matter passes through you constantly, and that its gravity is what holds the Milky Way together? And share this video with anyone who thinks the universe is mostly empty space. After this, they will understand that the invisible web connecting everything is far more real than it appears.